Hello students, today we will discuss about extending the MIPS pipeline to handle multi-cycle operations. So there are situations when some of the instructions cannot be completed, or some of the stages cannot be completed within the pipeline in a single clock cycle. So especially for floating point operations and all, for a single stage, it requires more than one clock cycle to finish that particular stage. So it is not always possible to finish a stage by using a single cycle alone for all the operations. So for this particular situation, we are considering the enhancement of the MIPS pipeline architecture to handle the multi-stage or multi-cycle operations. So these are actually dealing with the mainly it is dealt with the floating point operations. So when we consider floating point operations, we need to have such type of multi-cycle operations to be implemented. So normally it is impractical to recur all FP operations in MIPS architecture to complete the task or complete the stage in a single clock cycle, or not even in two clock cycles. So instead, the FP pipeline will allow for a longer latency for operations. So many situations, for the completion of the same stage of operations within the pipeline, normally the MIPS FP operations will take a longer latency. It will take more time to finish a particular stage operation for a special category of operations. So today we will be discussing about handling such multi-cycle operations related to the floating point instructions used in MIPS architecture. So initially we are taking some assumptions, like we are considering the FP instructions that are having the same pipeline as the integer instruction, but we are considering two major changes to the pipeline architecture. First change is the EH stage. The EH cycle may be repeated as many times as it is required. So normally FP operations will take more time to complete the task. So EH stage may not be completed within one clock cycle. So before moving into the next stage, the EH will be repeated more cycles or many times as it is required. So that is the first assumption we are considering for the multi-cycle operations. Then the second point is sometimes we can replace, or we can utilize more than one functional units for performing the task. That is called as, we are using multiple FP functional units. So, and if that units, if for the means the final execution, if we are using multiple functional units for the same thing, we can execute more things. So if you pipeline the same task that takes more than one cycle, we can even better the performance of the architecture by improving the pipeline outcome. So there are two assumptions. One thing is sometimes the stage to be repeated for more than one cycle, and sometimes we need to increase the number of functional units so that we can increase the performance of our processor system. So normally in these situations there is a chance of creation of stalls that will occur if the instruction that is to be issued will cause either a structural hazard or a data hazard. So as we have already mentioned in our previous sessions about when a stall may occur, it is only because of the non-availability of the functional unit or because of the non-availability of data. So in any of these situations there is a chance of the occurrence of stall. So when we use the MIPS pipeline architecture that is being extended for multi-cycle operations, we are considering the assumptions of having multiple cycles to be utilized at the same time or by the same operation, or the usage of multiple functional units to have the implementation of pipelining within the stage itself. So functional unit itself can be further being pipelined. So these situations will actually provide an extension to the existing MIPS basic architecture to produce such type of multi-cycle operations. So there is a chance of stall that may also happen in between because of the non-availability of functional units or the data that is required for the next set of instructions. So let us assume that our MIPS implementation consists of 4 separate functional units. For our imagination, just for explanation, first thing is the main integer unit. The integer unit that can be utilized for the normal load and store operation. That means the effective address calculation and all that can be done by using the integer unit, and it is also used for ALU, normal integer ALU arithmetic operations, and also used for branch related operations related to integers. Then second one is it is using another functional unit that is called as multiplier, that is for both floating point as well as integer. For both floating point and integer values we are using a separate functional unit called as multiplier for multiplication operation. Then third set is we are using floating point adder. We are using a separate functional unit, floating point adder, that handles floating point addition, subtraction and conversion operations. Similarly, fourth one is we are using a divider or division operation functional unit that is used for both floating point as well as integer data values division operations. It is used for both floating point as well as integer operations. So in this MIPS architecture, for MIPS implementation we are using 4 major units: one integer unit, then one multiplier unit, one adder unit and one division, and these are applied for both integer as well as floating point numbers. Now we assume that the different execution stages of these functional units are not pipelined. So initially we are taking this architecture where the functional units are not being pipelined. Assume that each of these units are available only once. So we are having one integer unit available, we are having one multiplier unit available, we are having one adder unit available, and we are having one divider unit available. Initial assumption is in this way, but we are actually going to change this structure into a pipeline format for the functional units. So the procedure of the pipeline stages will be in this particular format, that is starting from the first clock cycle to second clock cycle, then it will pass through the third and then fourth and fifth clock cycle. So first clock cycle, instruction fetch, instruction decode, then third clock cycle the EH stage will happen, then it will go to the memory stage, and finally it will go to the write back stage. So this is the normal flow in a pipeline architecture. So if somebody is wishing to execute some integer operation, it will go through this stage. Now if there is some multiplication operations that is to be done with both floating point and integer set of values, it will actually go through this path. Then if there is some floating point addition related operations, it will go through this path. Similarly, for division operations, it will go through this path. Okay, so EH is actually having multiple units, but different operations can actually share the same clock cycle for various types of operations. But here in this picture you can see that integer unit normally takes only one clock cycle to complete its normal operations, normal integer arithmetic or effective address calculation. It will take only one clock cycle, but other operations like FP or integer multiplication or FP addition or FP integer division operations, normally it will take more than one cycle. So that is why this rounds that arrow is given, because this cycle may not be completed within one clock cycle. Then it is to be continued for more than one cycles. Maybe it will last for 2 or 3 or 4 cycles for the completion of this particular operation. So when we do some multiplication, it may take more than one clock cycle. Similarly, when we do some floating point addition operation, it will also take some more clock cycles to complete its task by repeating the same execution stage for more than one clock cycles. And for the division also, it will do the same procedure. It may not be completed within a single clock cycle. It will be repeated for more than one clock cycle. So this is the problem with the basic MIPS architecture. Even if you are having multiple functional units, some units may take, especially for floating point operations and all, the units may take more than one clock cycle. So this is the basic structure that we are following for basic integer and other FP related operations with multiple clock cycles that is being utilized for the completion of the pipeline stages. Now, as EHC is not pipeline, so in our previous diagram, EHC is not pipeline. So everywhere in all the for all the functional unit, we are having only one EHC unit. No other instruction using that functional unit may issue until the previous instruction leaves the EH. If some other instruction wishes to access the same EH, it cannot be entered because even the previous instruction must be completed. So if it takes more than one clock cycle or some multiple number of clock cycles, the second instruction need to wait until the completion of the previous EH operation. If an instruction cannot proceed to the EH stage, the entire pipeline behind that will be stopped, or that will be in the queue. So as you know, if it cannot be ended, it will be in a waiting stage. The EH pipeline stage has some number of clock cycles that is always larger than 1. So normally for EH pipeline stage, especially for floating point operations, the clock delay will be mostly larger than 1 clock cycles. So we will consider we can generalize the structure of the FP pipeline in a different figure that is shown in a different figure by adding multiple number of stages into different functional units. So previous diagram, for each EH we are having only one functional unit available. If you modify that structure or generalize that structure into a different format, we can see the diagram in this format, where most of the time for integer unit we uses only one functional unit at a time, because normally it will take only one clock cycle. So only one integer unit will be available. But for multiplication, normally we are using, in the case of MIPS, we are using 7 different functional units for doing multiplication operation. 7 different functional units are being utilized. That means the functional unit for multiplication is divided into different stages. That's all. That means this can be pipelined. That means if one particular instruction is in M3, some other instruction can be in M2 or M1. So the stage, this multiplication operation can be pipelined. This functional unit can be pipelined by using different stages or different number of functional units for the same multiplication operation. Similarly, for addition, for FP adder also, we are using normally 4 different functional units that consist of the different stages starting from A1 to A4. 4 stages are there, and different instruction can utilize these different stages in different clock cycles. So this also indicates for 7 multiplication units, we can have 7 different clock cycles that can be utilized. For multiplication, we are considering the usage of 7 clock cycles. For FP adder, we are considering the usage of 4 clock cycles. So here the number of clock cycles or number of functional units can be extended to different stages, or these two can be pipelined. So multiplier can be pipelined and adder can also be pipelined. Then when it comes to divider, here we are not having multiple stages, so this is not pipelined. It is not pipelined. It is having only one functional unit, but the same functional unit takes more clock cycles, that is 24 clock cycles is utilized for completing the task of division. So just differentiate these four once again. The same diagram is being extended from a single functional unit into multiple functional unit for selected units. So for integer unit, we are having only one EH stage, only one unit available, which is usually taking one clock cycle. For multiplication, we uses 7 stages, so 7 units are being utilized, and it will be utilizing 7 different clock cycles for completing different stages of this multiplication operation. So multiplication will be divided into different stages and can be pipelined. Then addition is utilizing 4 different clock cycles, 4 stages, and the addition operation can be pipelined into 4 different stages. So different stages of addition can be distributed among these 4 stages. And for the division, we are having only one functional unit available, but it is scattered around, scattered into 24 different clock cycles. We are having only one functional unit available. If it starts, it should continue till the completion of that 24 clock cycle. Until that, no other can enter into the same operation. So at a time, only one can enter into the division operation. But for addition and multiplication, more instruction can be pipelined by utilizing different stages of these different units of multiplication and addition functional units. So this is the extended version of MIPS pipeline architecture. Now here for this particular assumption, we are actually considering 2 factors. One is the latency of the functional units, and the second one is the initiation or repeat interval of the different functional units. So 2 important terms to be considered in relation with the extended MIPS architecture with multi-cycle operations are latency and initiation interval. So as you know, latency is actually the time delay between 2 instructions. That means if one instruction produces a result and the second instruction expects that result, so how long it will take? What is the delay? Means how long the second instruction is waiting for getting the result of the first instruction. That is called as latency. So once again, the number of intervening cycles between an instruction that produces a result and an instruction that uses the result. So this is the instruction that produces the result, and this is the instruction that expects the results. So there is a gap between these two, this time delay between these two. It produces a result and it gets that result. If there is some latency, there is some delay, that can be called as the latency. That is the instruction that produces a result and an instruction that uses the result. So if it is not getting the result at the time when it arrives, it is to be waited. So it will be producing the result after some time. So up to that time, the next second instruction need to be waited. So that waiting time is called as latency. So the latency will affect the entire pipeline. Means the feature. The pipeline feature will be affected by the overall latency that is being produced by various insertions present in the entire pipeline architecture. So if the latency is being increased, automatically the performance of pipeline will also be affected. Then the second point is initiation or repeat interval. It is the number of clock cycles that must elapse between issuing two operations of a given type. When two operations of same type is given, two addition operation is being given, so how long it will take to start the second insertion. So the difference between these two, so normally if it starts from the first cycle, normally second will start from the second cycle. So automatically most of the insertion, the initiation or repeat interval will be one clock cycle, but not for all the insertion. We will see the difference. Normally if two insertions are given of same type, for like addition, two additions are given, so normally first will start at the first clock cycle, normally second will start at the second clock cycle with its insertion fetch operation. So we need to consider the latency and initiation or repeat interval for the explanation of this multi-cycle operation implementation in the MIPS pipeline architecture. So once again we will look at the diagram. So here we are passing through, for integer EX operation we are passing through this path. Then for multiplication we are passing through this path. Then for addition we are passing through this path. Then for division we are passing through this path. Okay, so any insertion. So if one insertion arises for multiplication, it will take this path. If one more multiplication arises, it will take the same path. There we need to consider whether it is depending on one another. It can be shared, but if more than one integer operation arrives at the same clock cycle, it cannot be done. But if more than one insertion arises for multiplication operation, they can share the different stages. If more than one insertion arises at the adder, they can share the stages, because these two are being pipelined. But for division, at a time only one can be ended, but that same division operation itself will take around 24 clock cycles to complete. So that much time any other insertion that is for the same operation need to wait for the completion of the division operation. Okay, so in this functional unit, by looking at the functional unit itself, we can understand that the divider is the most time consuming tasks when compared to other multiplication, addition or effective address calculation that is normally used with the insertion processing. So we need to consider the latency and initiation interval for the different situations. So we are having a table that indicates the various functional units that is already given in the previous diagram and its corresponding latency and initiation interval. So we had the integer ALU that is for normal integer related operations only. Then we are having data memory that is for load operations, especially for load. Store is also there. Data memory that is utilized for the integer and floating point load operations. That is also being done by the integer ALU itself. Then we are having a floating point addition, that is a separate functional unit. Then we are having FP multiplier, that is for floating point and integer multiplication operation, and FP divide functional unit that is used for division operation of integer as well as floating point numbers. So we look at the latency and initiation interval of all these functional units. Now you can see the latency of integer ALU is 0 and the initiation interval is 1. So first of all I will say what is initiation interval. By looking at the diagram, we will just see the initiation interval. What is initiation interval? If the same insertion is given once again, how long it will take to start the second insertion if two insertions are given at the same time. So Normally this is the path that is being followed for the integer operation. So first cycle, second cycle, third cycle, then fourth cycle, then fifth cycle. This is the normal flow for the integer operation, integer ALU. Okay, now the second instruction, normally it will start from the second cycle only, so it will start after one cycle delay. So that is why the initiation interval is 1. Now when we consider the latency is actually when we will evaluate latency when the second instructions expects the results of the first instruction. So first instruction is this one and second instruction is this one. First instruction will go through instruction fetch, decode, then EH, then after the end of EH stage it will produce the result. That is after the third clock cycle. Similarly, the second instruction arrives at second clock cycle. Then in the third clock cycle it will do instruction decode, and in the fourth I will write it here, fourth clock cycle it will enter into EH. In the EH stage it requires the result of the previous stage. So EH happens at the fourth stage and the results will be produced at the third stage. So just after the third stage it will produce the result, and when it arrives, the second instruction, when it arrives or enter into the fourth stage directly, it will get the result. So there is actually no latency here. See, from the third stage directly the result is given to the fourth stage where the execution stage of the second instruction arrives. So that is why the latency is given as 0 for the integer ALU operation. I hope it is clear. I am trying to explain that in a light way. Okay, so first instruction produces the result at the end of third clock cycle. Second instruction expects the result at the start of the fourth clock cycle. So there is actually no delay. Directly it will be getting the result by using the forward mechanism here. Initiation interval is 1 because after one cycle only the second instruction can start the execution. Okay, so I hope it is clear. First row of the table is clear, how to evaluate the latency and initiation interval. Okay, so this portion is clear. Now second is data memory, that is integer or FP load operation. Data memory, integer or FP load operation. So when this load operation will be finished, so which functional unit is utilized for load operation? The functional unit utilized is the same thing, that is the integer unit itself. So it will be going through the same path. First cycle instruction fetch, second cycle instruction decode, third cycle, then fourth cycle, then fifth cycle. It is passing through the same passage. So this is the first instruction, which is actually a load. So when the load will be completed, the effective address will be calculated here in the third cycle. Then in the fourth stage memory, that after the fourth stage, then only the load operation will be complete. So just after the fourth stage we will be having the result of load operation will be generated. Okay, now the initiation interval will be for the second operation, it will again be 1 because the second instruction can start after the one cycle delay only. So this is the second instruction. This is the first instruction. So instruction fetch, instruction decode, then in the fourth cycle it is expected to have the EH operation. But the problem is in the fourth stage the previous load is not being completed because after the end of fourth clock cycle only the load procedure will be completed. So the second instruction cannot do execution at 4th clock cycle, so it is to be lagged or delayed till the 5th stage. Okay, so instruction fetch, instruction decode, EX. Now it cannot be that because this is expecting the result of the previous instruction. So previous instruction result will be produced only after memory stage. But here memory stage is not completed. So this one clock cycle will be means that will be wasted, and in the next stage only it can do execution by taking the result from the memory stage of the previous instruction. So here there is a one clock cycle delay that is actually considered as the latency of this second instruction that is expecting the result of the first instruction. I hope it is clear. Once again, first instruction it will go through instruction fetch, decode, EX, memory. Then after memory stage it will produce the result of load or store, whatever it be, that operation. Then it will go to write back. So we are not giving importance to the write back now. Now second instruction arrives at the clock cycle 2, then instruction decode in the third clock cycle. It is expected to have EX at the 4th stage, but in the 4th stage the previous load is not completed. After the completion of load only it can do EX, so EX will be delayed till 5th clock cycle. So there is a delay here, one clock cycle lagging here. So that one is considered as the latency for the integer load operation. Okay, we will again look at the table for data memory operation. For data memory operation, here the latency is 1 and the initiation interval is also 1. Okay, so just I am explaining how these values are actually generated. Now we look at FP add operation. We look at FP add operation. FP add operation. So which path will be following? FP add, which path will be following? That is the adder. So we need to follow this path. We need to follow this path. So instruction fetch first cycle, second cycle, then this is the third cycle, fourth cycle, fifth cycle, sixth cycle, 7, 8. This is the way in which we are doing addition operation. So this is the first instruction that follows instruction fetch in the first clock cycle, instruction decode, then one portion of addition A1, then next portion at A2, A3, A4, different cycles. 4 cycles are utilized for finding the addition. Okay, so here first of all I will explain, if one more instruction arrives of same type, automatically the instruction fetch will happen at this stage. So there will be an initiation interval of 1 clock cycle. So that is again 1. Initiation interval is 1 here also. Okay, so after that instruction fetch, it will go for instruction decode here. So this is the path in which it should also follow. It is the path in which it should also, it is not with a division, okay, it is for the addition. So instruction fetch, second clock cycle, then third clock cycle it will go for instruction decode. Then it will go for EX, but it is expecting the result of addition, but the result of addition will be generated only after the 6th clock cycle, that is only after completing the stage A4 the result will be produced. But it is expecting the EX stage at here. It is expecting the EX stage here. But here it cannot enter into EX stage because the previous stage result is not being obtained. So this 3 clock cycle 4, 5 and 6 will be wasted, and in the next stage, 7th stage, it will be getting the result. So 3 clock cycles are being wasted. So this 3 is actually considered as the latency of floating point adder here. I hope it is clear. For instruction. For the first instruction, instruction fetch decode, then 3 4 5 6 the various stages of addition, then it will produce the result, then it will go to memory and write back stage. Second instruction, second clock cycle instruction fetch, third clock cycle instruction decode, fourth clock cycle it is expecting EH but the result is not available, so it is to be waited until the completion of sixth clock cycle. So 4 5 6 3 clock cycles are being that is wasted, or that is the waiting period to move to the next clock cycle for the EH stage. That is totally 3 clock cycle to be waited. So that value is considered as the latency of FP add operation, that is 3, and the initiation interval is 1. I hope it is clear. When compared with the previous two, it is also clear, I think. Okay, so why this value 3 and why this value 1? Now when we look at FP multiplication or integer multiplication operation, so which path will be followed for multiplication? Which path will be? So this path will be followed for multiplication for integer or floating point multiplication. So first clock cycle, second clock cycle, then 3 4 5 6 7 8 9 10 11. So this is the first instruction. Then second instruction, normally it will start from the second clock cycle starting with instruction fetch. So there is an initiation interval of 1, that is again 1. So here for initiation interval we are considering the same instruction being repeated once again. Now instruction fetched at second clock cycle, then instruction decode at third clock cycle, then we expect EH here. We expect EH here, but the instruction expects the result of the previous instruction. It will be generated only after the 7th clock cycle. So here it cannot be done. It is to be waited till the completion of all these 6 clock cycle, then only it can go for EH. So 1 2 3 4 5 6 clock cycles is being lagged. This is considered as the latency here. Once again, for FP or integer multiplication, normal first instruction it will pass through 11 clock cycles for instruction fetch decode, then M1 M2 M3 M4 M5 M6 M7 for various stages of multiplication, then it will go to 10th and 11th stage. Similarly, for the second instruction it will arrive at the second clock cycle, then decode at the third clock cycle, fourth clock cycle it can go for EH, but it is actually expecting the result of the previous one. So the result will be obtained only after the 7th stage. So 6 clock cycles will be wasted, and 6 is considered as the latency of the operation FP multiplication. So here the latency is 6 and the initiation interval is 1. I hope it is clear for FP multiplication. For all these we are following the same pattern. For all these type of operations we will consider one more which is slightly different, that is FP divide, and also for integer division operation. So which path will be followed for this one? The path followed is FP division. This path will be followed for division operation. So first clock cycle, second clock cycle, then we are having only one functional unit. We are having only one functional unit which consists of 24 clock cycles. So 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26. Then 3 to 26 clock cycles are actually given for that single functional unit which is used for the division operation. Then this is 27 and this is 28. Now the specialty of this FP or integer divider is that this is not being pipelined. This is not being pipeline. This is considered as only a single functional unit. When somebody enters unit, no other operations can be done for the case of division operation. So this is the first instruction that will go through this path. Okay, so automatically when this will produce the result, it will produce the result only after the completion of this division, this entire. So this is totally 24 clock cycles for the completion of div. So here the result will be produced. Now a new instruction arrives, instruction fetch. Okay, then instruction decode. Actually this division is not being pipeline, so that is why after instruction fetch it is to be waited until the completion of the entire previous instruction. Okay, so the entire thing to be, that means for the second instruction, the first instruction need to wait until the completion of the entire 24 clock cycles. So the clock cycle is given, means the latency is given as 24. The entire division period is actually required for the waiting. There is a latency of 24 clock cycle. And now the initiation interval is, you might be imagining, one is there already. Then instruction fetch. So the problem is totally only instruction fetch is being completed, then again 24. So because we did not evaluate the decode operation, after some time when the same instruction to be repeated, after some time it is to be started with instruction fetch again. Okay, so that is why here the initiation interval is given as total this 24 plus 1. 25 is given as the initiation interval, because the entire process to be started again after this much gap. Again that is to be started. So it is not the exact value, that is so sometimes there will be a confusion like whether this first one is also being considered or not. Okay, so that is actually a confusion, but just imagine that as it is not entered into the further stages, that situation the instruction to be restarted from the instruction fetch itself once again. So this entire period will be lost. So here the value is given as 25 as the initiation interval. So 24 is the latency, that is the entire number of cycles utilized for division, and the initiation interval plus the repetition of the instruction fetch once again, that period is being wasted for the starting of the execution, because the instruction decode is not being done. That's why everything is to be repeated again. So initiation interval is more for the case of the division operation. So just assume that this is the situation when we are using multiple functional units, and initially we were discussing about multiple functional units only available that can be executed within a single clock cycle, but we have taken the assumption like some of the operations like FP operations cannot be completed within one clock cycle. Normally it will be repeated for more than one clock cycle. Then in order to make it easier for the MIPS architecture, they have implemented a multi-cycle operations along with multi-stages, multiple functional units for individual EH stages. So the EH stage can also be pipelined by dividing the various stages of multiplication or addition operations of various floating point and integer values, so that more operations can be executed simultaneously, even with having some delay or latency in the execution of two different operations. So we have seen the new mechanism for implementing the MIPS or extending the MIPS pipeline architecture by using multiple multi-cycle operations, and how we can handle the multi-cycle operations for various functional units and various instructions that are entering simultaneously into these systems. And these latency and initiation interval and the execution of these stages by using these multiple functional units or multi-cycle operations are helpful for evaluating various other things related to the insertion level parallelism also, that will be described in detail in the remaining or continuing or next sessions, that is yet to deliver. So these portions are that is to be considered as an important one. So just understand the latency and initiation interval that is applied to various functional units, which is in a multi-cycle operation format available with the MIPS pipeline architecture. So that's it for now. We will continue with the insertion level parallelism and other approaches used in insertion level parallelism in the next session. Thank you.